Okay. Now it's working. Okay, good. So let's start from having a look at the motivations that pushed the development of this research. I mean, this is common knowledge for all of you. If we look at the last 2 decades of deep space exploration, so we see 2 parallel trends. The first one is the one that characterized the exploration of small bodies in the solar system, and the reason are mainly 3, because they can be used to exploit resources on the surface that may be rare on Earth, because of planetary defense reason, and because of scientific understanding of these bodies, because they may contain information on the origin and formation of the solar system. In parallel to that, we see, if we look at the number of CubeSat and miniaturized spacecraft that have been launched in the last 20 years, we see an exponential growth. And even if so far these missions have been used mainly on Earth orbit, we are now extending the exploitations of these platforms for deep space applications, with missions to the Moon, Mars, and the small bodies. And the reason is that they can be used to perform riskier, cost-effective solutions at relatively low cost, indeed. Now, the issue in performing proximity operations to small bodies is, of course, that the dynamical environment is extremely nonlinear, highly perturbed, often in some cases, such as the Didymos dimorphos binary system, the dynamics is dominated by solar radiation pressure, and is affected by many uncertainties in navigation, control, and knowledge of the environment. So from an engineering perspective, there is the need of improving autonomies for these capabilities. Now, I added this slide. This wasn't inside the original presentation. So this is the ESA's technology CubeSat fleet. These are the main CubeSats that ESA is the European Space Agency is working on. And if you look on the right, you can see 3 different mission concepts. The first one on which we are actually contributing, we are actually working on. So the first one is Milani. We will talk about this during this presentation. I will give you a more detailed overview on this. Milani will be one of the 2 CubeSat that will be carried on board the Hera spacecraft. Hera, as you probably know, is the dual counterpart to the DART mission in the IDA program. Lumio is a lunar observer. This one on the bottom right of the slide is a lunar observer that will perform scientific observation of the lunar far side from a quasi-halo orbit on the Earth-Moon L2 point. And the objective of the mission is to observe and characterize the meteoroid impact on the lunar far side. And then Margo will be the first standalone CubeSat to reach autonomously an asteroid. So we will go back on Milani a little bit more in details in the next slides, because the methodology that I've been developing, I try to apply the methodology that I've been developing to the Milani concept. Okay, so goal-oriented proximity guidance. When we look at the literature, when we look at ways of solving guidance problems in astrodynamics, what we see is that typically these problems are solved, are formulated as an optimal control problem solved in some way. And the idea is often to minimize either the fuel consumption or the time of flight required to go from an initial state to a final one, while respecting some constraints. Now, when we face the problem of performing proximity operations to small bodies, this may not necessarily be the case, because we may be interested, because typically the proximity dynamics is highly connected, the configuration space is highly connected, meaning that we can actually move from one position in the asteroid frame to another one with a very low fuel consumption, because the gravity field is maybe very low, very weak. And moreover, we may be interested in maximizing the scientific outcome of the mission instead of the fuel or time consumption. We may not even have a final state, a specific final state that we want to reach. So that's why we formulated this problem as a sequential path planning problem, in which we want to maximize the opportunities to perform goal achievements. And this can be, for example, the observation of a feature on the asteroid surface. Okay, so this feature is then mapped into a certain observation region. So this, through observation requirement, this feature is mapped into a given observation region. And the idea is that we want to maximize the goal achievement of that observation, while of course being compliant with the operational constraints. We don't want to impact on the asteroid, we don't want to escape from the system. And for example, we don't want to cross some region of the system. For example, we don't want to go in the night side of the asteroid. Many concepts for proximity operations, autonomous proximity operations, rely on autonomous navigation techniques. And these often are based on are founded on vision-based navigation systems, which can, of course, be impacted by a long transition in the spacecraft night side. So one of the other operational constraints that we imposed is to be in the day side of the asteroid. And then, of course, we want to respect some control constraints. So we have a limited control capability on the spacecraft. So we want to respect, we want to find a solution within that, that control domain. So what we did is basically defining an objective function, a cost function that is somehow proportional to the time spent within this observation region, given by our requirements. There is also a contribution in the cost function related with the fuel consumptions. If you're interested, we can talk about this. It's described on the paper. And so the optimization problem becomes the minimization of this cost function, or well, minus this cost function, but it's the same, in terms of the optimal control and the next maneuvering time, while respecting the differential constraints, the dynamics of the mission, and the operational constraints that we imposed. In particular, we look at the solution within the intersection of two sets in the control domain. The first one is the science set, the one that we call the science set, that generates trajectories that cross the observation region, and the other one is the admissible set that generates trajectories that remain in the operational range. The numerical methodology used to solve this problem at this stage is the one of is a sample-based method. Similar approaches have been developed in literature by researchers such as David Surovic or Francesco Capolupo, and they consist in performing this abstract reachability analysis on the control domain. So the methodology is the following: an initial sampling of the control domain, a rough initial sampling of the control domain is performed. For each sample, the trajectory is propagated forward in time and mapped into an abstract space. That can be, and we will see some different example in the following. Then on this space, some sort of cost function, scoring function is defined. And this allows basically to generate a map of the cost function over the initial sample of the initial control domain. Then an heuristic-based mesh refinement is used to refine the mesh, because of course it's untrackable from a computational point of view to perform a fine research on the control domain. So an heuristic-based method is used to refine the mesh in the area of most interest. By repeating this procedure for a certain number of iteration cycles, what we can obtain is this kind of abstract reachability map. So this is what you see here is the control domain, and you can clearly see that we have a mesh refinement in a specific area of the control domain where the score function in terms of science is maximized. And this operation is repeated sequentially over the mission to generate the full mission profile. Now, to estimate, to value the quality of the generated trajectory, we define a metric that is a sort of non-dimensional time spent within the observation region. So basically, when G is 1, the mission has just started. When G is 0, the mission has just started. When G is 1, the mission is completed. Now, the cool thing about this approach is that depending on the way, the form, and the space in which the observation region is defined, different operational approaches can be obtained, as we will see in the following. So now we will see at least 3 application scenarios. There are actually 4. If we have time, we can go through the 4th one, but otherwise we will stick to the 3 that I presented at the conference. They are all applied to the Milan emission concept. As I briefly mentioned before, Milan is a 6U CubeSat, will be carried on board the Hera spacecraft and released in proximity of the Didymos binary system at the beginning of 2027. Our research group is responsible for the mission analysis, GNC, and image processing design for the platform. The mission successfully passed the PDR last summer and is currently in phase D. And yeah, the project is of course developed under Rizza contract, and the prime contractor is Tyvak International. We are providing the software for GNC and image processing and designing the mission analysis. The first application scenario is the one regarding the global mapping of the main asteroid of Didymos. In this work, I will refer to Didymos, which is the main attractor, as D1, and with Dimorphos, which is the secondary asteroid, as D2. So this is achieved by basically taking a shape model of the asteroid and discretizing it to define a certain feature on the surface. At this stage of the methodology, the approach is assuming that we know the shape of the body. So we define a certain number of features on the asteroid surface, 96 in particular. For each of these features, we define some observation requirements in terms of range, declination of the spacecraft over the feature which we want to perform the observation, and illumination conditions expressed as declination of the sun over the surface. And we also specify that we want to observe each feature for a given amount of time, 1 hour in this case, in order to maximize the opportunities of observation. Now, because of the geometry of the system, it was impossible to impose a stringent illumination condition on the entire asteroid surface. So we basically define a differential observation constraint for the delta sun parameter, with more stringent requirement on the equatorial region and more weak requirements on the polar regions because of the lower illumination conditions, because of the worst illumination condition. So when these observation requirements basically are translated into an observation region that in the inertial space has the shape of a rotating section of a cone over the feature, exactly. And this is a time-dependent region. Now, if we map this region into the abstract space, so if you recall the path of the methodology that we've seen before, we are mapping now this section of a cone into an abstract space, which is the space of the measurements, so range, declination of the spacecraft, and declination of the sun. This becomes now a time-independent observation region in this space, and we want to maximize the time that we spend within this set. We perform the Monte Carlo simulation, selecting 500 samples with a uniform initial spatial distribution and Gaussian initial velocity in the operative range of the system, so in the dayside range of the system. And then we run the simulation for all. We run the Monte Carlo for all the trajectories, and what we obtained is that we can see that in less than 20 days, all the trajectories perform global mapping, global coverage of the asteroid. Now, of course, this is very computationally expensive because for each of the trajectory we need to map the trajectory in the abstract space of each feature. So maybe untrackable, maybe a bit burden from a computational point of view. So one may say, okay, but why don't we define an inertial observation region in front of the asteroid instead of characterizing and defining the features on the surface of the asteroid? We try to do this in the second application scenario. We defined, this time we define only one feature, which is centered at the center of the asteroid. And we impose observation requirements in terms of range and phase angle on this feature. To compare these results with the previous application scenarios, we are using still the 96 feature observation model, because we actually want to see, by using this simplified approach, how much of the effective global mapping we can perform. And I mean, as we expected, not all of the, so we used the same initial samples of the previous Monte Carlo. As expected, not all the trajectories reaches convergence. But what we found very interesting is that without knowing the feature distribution on the asteroid surface that are to be mapped, more than almost all the trajectories reached more than 80% of the global coverage in a similar amount of time, with, of course, a much lower computational cost on board. The third application scenario is the one in which we want to observe this time a single feature. So we don't want to perform global mapping. We want to observe a single feature on the surface of the secondary asteroid, on the surface of D2, namely the dart impact crater on the asteroid. Of course, this analysis is performed with the pre-impact knowledge of the target. Now, shape models are being updated. The trajectories of the bodies is being updated, but this will work just as an application test case. So we want to observe this feature on the surface of D2, imposing range, declination, and illumination conditions. Now, the parameters used both in this case and in the scenario one were actually taken from the scientific requirements that we had with the Milan mission. Now, what you can see here is that while with respect to previous cases, here we have a feature that is rotating with the secondary asteroid, and the asteroid itself is rotating about D1. So this is a very time-dependent region, and when we look for in the reachability analysis, we look for the intersection between the science and the admissible region. It may happen that this set is actually the null set. We don't have any valid solution within the given time horizon. So to bypass this problem, we thought of combining the first two approaches. Trying to track the feature on D2 with the first approach, with the rotating approach. And if no solution was found, we switched to an inertial-based observation region. And this basically works as a rephasing mechanism that allows the secondary asteroid to perform a revolution about D2. This is an example of the results that can be obtained. What can be seen is that the global coverage of the feature takes much more than previous case, but still is able of reaching global observation of the feature. And the other thing is that if you remember, we imposed an operational requirement on the phase angle of the spacecraft, and we said that we don't want to go in the night side, but actually we imposed the constraints that was we don't want to go with a phase angle that is larger than 120 degrees because we wanted to have some margin. And actually, what the result of this analysis is that the optimal trajectory that is found by the algorithm is actually very close to a terminator sun-synchronous orbit, which is exactly the final approach phase that our team designed for Milan. So this was very interesting because without any knowledge on the actual trajectory, the optimal solution found in this way was actually a set of close orbits about the system in close proximity.
Even the lighting is optimal in Sun 6.
it clearly is not optimal, but I mean, because
you have a constant lighting, like
yes, but you have different illumination constraints on the feature. So it's you have a constant lightening. This is true, but it's not given that is the one that you want to have on the feature. So I mean, we found this being an interesting result. Then, if you want, we can also go into the fourth application. The fourth application basically imposes an additional constraint that is the one of a given maneuvering schedule. So we imposed a maneuvering pattern that was compliant with operations on ground by imposing that we performed a maneuver after 3 days and then a maneuver after 4 days to be compliant with the ground working week. And we also performed a comparison between the performance of the trajectory obtained with this approach and the performance obtained with the Milani nominal mission profile. So we, just to conclude, we defined a flexible framework to perform goal-oriented proximity operations. Of course, this is still at a very preliminary stage. Everything is in open loop. Navigation and uncertainties are not included. And one of the major issue of this approach, while being partially solved by a smart selection of the observation region, is the computational cost of the algorithm. So and this leads us to what I will be trying to do while staying here. I will try to reformulate the problem to cut the part of the heuristic mesh refinement and at least the part of the heuristic mesh refinement and substitute it with a more optimal approach. I will introduce uncertainties inside the problem formulation, and this, apart from being extremely important for robustness, will also pave the path to the third activity that we want to perform here, which is extend this methodology to the SNAC framework. And then it's not stated here on the slide, but we also been working with we're starting to work with Jeff on the understanding of the Tron facility to perform some hardware in the loop validation of the approach. And so this concludes my presentation. If you want, we can go a little bit more into the details of something. And yeah, if you have any question, I'll try and I'll be happy to answer them.